On October 19, 2017, a Canadian astronomer named Robert Warwick noticed something that shouldn't exist. A dot of light moving through telescope data, traveling impossibly fast through our solar system. By the time anyone realized what they were looking at, it was already leaving. This object, which scientists would name Oumuamua, was the first confirmed visitor from beyond our solar system. And nothing about it made sense. The discovery happened at the Pan-STARRS 1 telescope in Hawaii, a facility specifically designed to scan for near-Earth objects that might pose a collision risk to our planet. The telescope sweeps the night sky methodically, comparing images taken on different nights to detect anything that moves. Most of what it finds follows predictable patterns. Asteroids orbit the Sun in elliptical paths. Comets swing in from the outer solar system, develop their characteristic tails as they approach the Sun's heat, then retreat back into darkness. Oumuamua did none of these things. When Warwick first spotted it, the object was already 33 million kilometers from Earth, roughly 85 times the distance to the Moon. More importantly, it was moving away from us at tremendous speed, having already made its closest approach to the Sun 40 days earlier on September 9th. This timing presented an immediate problem. Astronomers had missed the object's arrival entirely. They were watching it leave. The Hawaiian research team chose the name Oumuamua, which translates roughly to "a messenger from afar arriving first" in the Hawaiian language. The name carried weight beyond its poetic quality. This wasn't just another space rock drifting through the cosmic neighborhood. The mathematics of its trajectory revealed something extraordinary. Oumuamua's velocity was 26 kilometers per second relative to the local standard of rest, the average motion of stars in our galactic neighborhood. That speed, combined with its path through space, meant one thing with absolute certainty: this object originated from another star system. Scientists created a new classification system on the spot. Traditional designations use letters and numbers to catalog asteroids and comets based on when and where they were discovered. Oumuamua needed something different. It became 1I, marking it as the first interstellar object ever identified. The I designation was invented specifically for this discovery, a formal acknowledgement that astronomy had entered new territory. The scientific community had exactly 4 months to study Oumuamua before it faded beyond detection. 4 months to point every available telescope at this visitor, to gather whatever data they could before it disappeared forever into the darkness between stars. What they observed during that narrow window would spark debates that continue today. Shape presented the first puzzle. Direct observation was impossible. Even through the most powerful telescopes on Earth and in space, Oumuamua appeared as nothing more than a point of light, a single pixel against the black. Scientists couldn't photograph its surface or measure its dimensions with any conventional method. Instead, they watched how its brightness changed. As Oumuamua tumbled through space, it reflected varying amounts of sunlight toward Earth depending on its orientation. These brightness variations were extreme. The object's light intensity changed by a factor of 10 as it rotated every 7.3 hours. No asteroid or comet from our solar system exhibits such dramatic variation. The numbers suggested something with a shape unlike anything we'd encountered before. Astronomers led by Karen Meach analyzed the light curves, the graphs showing brightness over time. Their calculations pointed toward an object that was extraordinarily elongated. The estimates varied, but Oumuamua appeared to be somewhere between 100 and 400 meters long, while its width measured only 35 to 167 meters. The aspect ratio, the relationship between length and width, exceeded 10 to 1. Imagine a cigar's shape, but more extreme than any natural object we'd ever documented. Some researchers suggested an alternative interpretation. Perhaps Oumuamua wasn't cigar-shaped at all, but instead resembled a pancake, an extremely flat oblate spheroid tumbling end over end. Both shapes could produce the observed brightness variations. Without direct imaging, distinguishing between these possibilities proved impossible. The color added another layer to the mystery. Spectroscopic analysis, which breaks down the light reflected from an object to determine its composition, revealed that Oumuamua had a distinctly reddish hue. This coloring resembled objects from the outer regions of our own solar system, things like Kuiper belt objects that orbit beyond Neptune. The red tint suggested a surface that had been exposed to cosmic radiation for an immense period, possibly hundreds of millions of years. Cosmic rays, high-energy particles that pervade interstellar space, gradually alter the chemistry of exposed surfaces, turning them this characteristic color. The surface composition pointed toward a dense, rocky body possibly containing metals. Critically, there appeared to be no water ice present, at least not on the surface. This observation would become important later, when Oumuamua's behavior started contradicting its apparent nature. But the truly strange characteristic was the tumbling. Oumuamua wasn't rotating smoothly around a single axis like most objects in space. Instead, it exhibited what's called non-principal axis rotation, a chaotic tumbling motion where the object spins in multiple directions simultaneously. The light curves didn't repeat exactly from one rotation to the next. The double-peaked periodicity that astronomers measured kept showing slight inconsistencies. This tumbling motion typically results from violent events. A collision, perhaps in the object's distant past, could impart this kind of complex rotation. Once started, the tumbling would persist for extraordinarily long periods. The timescale for this motion to naturally dissipate through internal friction exceeds 1 billion years. Oumuamua's tumble was a fossil, a preserved record of some catastrophic encounter that happened in another solar system, long before this object ever reached ours. Scientists traced the trajectory backward, running the orbital calculations in reverse to determine where Oumuamua came from. The initial results pointed toward Vega, a bright star in the constellation Lyra, located about 25 light-years from Earth. However, this connection proved illusory. Given Oumuamua's velocity, the journey from Vega would have taken roughly 300,000 years. When astronomers accounted for stellar motion over that time span, Vega wasn't anywhere near the calculated origin point when Oumuamua would have passed through that region of space. The velocity profile itself revealed something fascinating. Oumuamua's speed closely matched the local standard of rest, the average motion of matter in our section of the Milky Way galaxy. This similarity suggested the object might have circulated through the galaxy multiple times, possibly originating from an entirely different region of the galactic disk before eventually wandering into our solar system's gravitational influence. Further analysis ruled out the dozen closest star systems as possible sources. None of them aligned with the trajectory when accounting for their motion through space over the relevant timescales. Oumuamua's origin remained, and remains, unknown. As September turned to October and November, telescopes around the world tracked this mysterious visitor. The Hubble Space Telescope, the Very Large Telescope in Chile, the William Herschel Telescope in the Canary Islands, all of them focused on this receding point of light. Astronomers knew they were watching something unprecedented slip away. By January 2018, Oumuamua had faded beyond detection. It was still out there, still traveling through our solar system, but too dim and too distant for even space-based telescopes to observe. The object continues its journey today, currently beyond Jupiter's orbit and moving at roughly 70,000 miles per hour relative to the Sun. In approximately 4 more years, it will cross Neptune's orbital path and return to interstellar space, never to be seen again. What scientists gathered during those 4 months of observation would fuel years of analysis and debate. Because as researchers examined the data more closely, they discovered something that transformed Oumuamua from an unusual interstellar asteroid into something far more perplexing. The object was accelerating in ways that gravity alone couldn't explain. The object was accelerating in ways that gravity alone couldn't explain. Marco Micheli at the European Space Agency's Near-Earth Object Coordination Center noticed it first. High-precision measurements of Oumuamua's position showed deviations from purely gravitational motion. Something was affecting the object's trajectory beyond the gravitational forces of the Sun and planets. The team ran the calculations repeatedly, checking for errors, calibrating their instruments, searching for any mundane explanation. The signal remained. On June 27, 2018, they published their findings. Oumuamua was experiencing non-gravitational acceleration, detected at 30 sigma significance. In statistical terms, this wasn't a marginal detection or a possible artifact. It was unambiguous. The magnitude wasn't enormous. During the period near closest approach to the Sun, the accumulated velocity change amounted to roughly 17 meters per second. For an object traveling at tens of thousands of miles per hour, this represented a relatively small perturbation. But it was there, measurable and consistent. Astronomers recognized this signature immediately. Comets behave this way. As they approach the Sun, volatile ices sublimate from the surface, releasing jets of gas and dust that create a subtle rocket effect. The comet gets pushed slightly off its purely gravitational trajectory. This phenomenon is well documented and routinely observed in cometary motion. Except Oumuamua showed no cometary activity whatsoever. When comets pass near the Sun, they develop a coma, a fuzzy envelope of gas and dust surrounding the nucleus. They often grow tails, spectacular streams of material pushed away by solar radiation and the solar wind. These features are the visual signature of a comet's transformation as solar heating drives volatiles from the surface. Astronomers had looked for these features. The Very Large Telescope in Chile took extremely deep stacked images specifically designed to detect even faint cometary activity. The images showed nothing. No coma. No tail. No visible ejecta of any kind. This created an impossible situation. The object was accelerating like a comet but looked nothing like one. Researchers proposed radiation pressure as a potential explanation. Sunlight itself carries momentum. When photons strike an object's surface, they impart a tiny push. For small objects with large surface areas relative to their mass, this pressure can produce measurable acceleration. The mathematics worked out initially. If Oumuamua had the right mass-to-area ratio, solar radiation pressure could account for the observed acceleration. But this solution created its own problems. For radiation pressure to work, Oumuamua would need to be extraordinarily thin. The calculations suggested a thickness of less than 1 millimeter. Given its estimated length of several hundred meters, this would make the object essentially a cosmic sheet, a fragment with dimensions unlike anything in the known solar system. Some researchers explored whether Oumuamua could be a fragment of a larger body, torn apart by tidal forces during a close stellar encounter. This tidal fragmentation scenario provided a mechanism for creating elongated, flat objects. When a celestial body passes too close to a star or massive planet, gravitational gradients can literally rip it apart, producing fragments with unusual geometries. The theory had merit. Calculations demonstrated that stellar tides could efficiently produce Oumuamua-sized pieces from various progenitors, long-period comets, debris disks, even disrupted planets. These fragments would then be ejected into interstellar space, wandering the galaxy until chance brought them into another star system. This explanation accounted for the shape. It provided a formation mechanism. But it didn't fully resolve the acceleration mystery. Other theories emerged. Some researchers suggested Oumuamua might be composed of nitrogen ice, similar to the surface of Pluto. As this exotic ice sublimated near the Sun, it could produce acceleration without creating a visible coma. The nitrogen would be transparent, unlike the dusty clouds that make typical comets visible. Testing this hypothesis proved difficult. The observational window had closed. By the time these ideas were developed and debated, Oumuamua had receded beyond the reach of our instruments. Then in May 2020, researchers proposed something more radical. What if Oumuamua was a hydrogen iceberg, a body composed of solid molecular hydrogen formed in the extreme cold of giant molecular clouds where temperatures hover near absolute zero? The hypothesis was elegant. Hydrogen ice could sublimate as the object warmed, producing acceleration. Being nearly transparent, hydrogen outgassing wouldn't create a visible coma. The theory seemed to solve every puzzle simultaneously. Except it didn't survive scrutiny. Follow-up analysis revealed a fatal flaw. Hydrogen icebergs cannot survive their journey through interstellar space. Starlight heating would destroy an Oumuamua-sized hydrogen ice body within roughly 10 million years. Collisional heating in the object's birthplace would pose additional problems, potentially destroying such structures before they could even escape into the interstellar medium. The journey from Oumuamua's point of origin to our solar system likely took hundreds of millions of years. A hydrogen iceberg simply couldn't make that trip intact. Throughout 2018 and into 2019, the scientific community grappled with these contradictions. Each explanation solved some aspects of the mystery while creating new problems. The object's behavior remained stubbornly resistant to simple classification. Some researchers began questioning fundamental assumptions. What if the standard models of comet composition and behavior were incomplete? What if interstellar objects operated under different rules than solar system natives? The debate took an unexpected turn in October 2018 when Harvard astronomer Avi Loeb and his postdoctoral researcher Shmuel Bialy published a paper exploring an unconventional possibility. They suggested that Oumuamua's characteristics could be explained if it were an artificial object, specifically a thin solar sail accelerated by radiation pressure. The hypothesis was not presented as a definitive claim but as an exploration of possibilities given the unusual observational constraints. A lightweight, artificial structure designed to harness radiation pressure would naturally exhibit the observed acceleration without cometary outgassing. The extreme thinness required by the radiation pressure calculations would make sense for an engineered sail rather than a natural object. The proposal generated immediate controversy. Most astronomers found the artificial hypothesis unnecessary and implausible. Several problems undermined the solar sail interpretation. A tumbling object wouldn't accelerate efficiently from radiation pressure. The chaotic rotation would average out the directional force, preventing sustained acceleration in a consistent direction. Moreover, invoking an alien artifact to explain a single unusual observation violated a principle scientists hold dear: extraordinary claims require extraordinary evidence. The available data, while puzzling, didn't necessitate abandoning natural explanations. The debate revealed something important about how science processes anomalies. When observations don't fit existing models, researchers face a choice. They can propose modifications to known physics and chemistry, extending familiar principles into new regimes. Or they can invoke entirely new phenomena, whether natural or artificial. The scientific community generally prefers the former approach. History shows that most astronomical mysteries eventually yield to conventional explanations, often requiring nothing more exotic than better data or refined models. By mid-2019, most astronomers had concluded that Oumuamua was likely a natural object, though its precise characterization remained contentious. The limited observation window meant definitive answers might never emerge. The object had delivered its secrets incompletely, leaving researchers to work with fragmentary data and competing interpretations. But the story wasn't finished. In 2024, astronomers made a discovery that recontextualized everything they thought they knew about Oumuamua. They identified 14 additional asteroids exhibiting the same unusual behavior, non-gravitational acceleration without visible cometary activity. These objects weren't interstellar visitors. They orbited the Sun, members of our own solar system's population. Yet they showed the same puzzling characteristics that made Oumuamua so enigmatic. This discovery prompted the creation of a new classification, dark comets. These objects accelerate like comets but remain visually indistinguishable from asteroids. No coma, no tail, no obvious outgassing. Just subtle deviations from purely gravitational motion. Oumuamua became the first known member of this class. Not unique after all, but the initial example of a phenomenon that occurs in multiple stellar systems. The dark comet classification didn't immediately solve the mystery of what causes the acceleration. But it transformed the question. Instead of explaining one bizarre interstellar anomaly, researchers now confronted a broader question about a whole population of objects with similar properties. What mechanism could produce non-gravitational forces without visible outgassing? The answer would come in 2023, from researchers who approached the problem from a completely different angle. They started by asking what happens to a comet during its long journey between the stars. Jennifer Bergmer and Daryl Seligman approached the puzzle differently. They didn't focus on what Oumuamua was doing during its brief passage through our solar system. They focused on what happened before that. During the hundreds of millions of years it spent drifting through interstellar space. Space between the stars isn't empty. It's filled with cosmic radiation. High-energy particles moving at nearly the speed of light, constantly bombarding any object unfortunate enough to cross their path. These particles carry enough energy to break molecular bonds, rearranging atoms and creating new chemical species. What happens when cosmic radiation hits water ice? The energetic particles slam into water molecules, H2O, breaking them apart. Sometimes the fragments recombine into water. Sometimes they form something else entirely. Molecular hydrogen. H2. This process occurs constantly in space. Radiation processing transforms ice chemistry over geological timescales. But here's what makes it interesting: molecular hydrogen is small. Really small. Small enough to become trapped within the ice matrix itself, nestled between water molecules in tiny voids and cracks. Bergner's team ran calculations. If Oumuamua started as a normal water-rich comet and traveled through interstellar space for long enough, cosmic radiation could convert up to 30% of its water ice into trapped hydrogen. That's not a trivial amount. That's a significant reservoir of volatile material locked inside the ice. Now imagine that hydrogen-rich comet approaches the Sun. As it heats up, the ice begins to sublimate. But it's not just water vapor escaping. The trapped hydrogen, warmed and energized, starts to vent from the ice. Molecular hydrogen is extraordinarily light. Far lighter than the carbon dioxide and water vapor that typically drive cometary jets. When hydrogen escapes from warming ice, it produces thrust. The outgassing pushes the comet, creating exactly the kind of non-gravitational acceleration observed in Oumuamua's trajectory. But here's the critical detail: molecular hydrogen is so light that it can't drag dust particles along with it. Water vapor and carbon dioxide have enough mass and momentum to carry dust grains, creating the visible coma and tail we associate with comets. Hydrogen doesn't. It escapes cleanly, invisibly, leaving no observable trace. This explains everything. The acceleration without a coma. The comet-like behavior without comet-like appearance. The whole paradox resolves if Oumuamua was simply a hydrogen-rich comet, processed by cosmic radiation during its long journey between the stars. The numbers worked. The team's models showed that the amount of hydrogen needed to produce the observed acceleration matched the amount that cosmic radiation could plausibly generate. The timing worked too. Release the hydrogen as the object approaches the Sun, and you get exactly the acceleration profile that astronomers measured. Daryl Seligman put it simply: this theory explains every single weird aspect of Oumuamua. Marco Micheli from the European Space Agency called it the most convincing model so far. The hydrogen outgassing hypothesis didn't require exotic materials. It didn't invoke alien artifacts. It just extended known chemistry into a new context. But acceptance wasn't immediate. Science moves carefully, particularly when resolving high-profile mysteries. The hydrogen theory needed to survive scrutiny. Could hydrogen really remain trapped in ice for hundreds of millions of years? Would it escape too quickly, leaving the comet depleted before it ever reached our solar system? The researchers addressed these questions through detailed modeling. Hydrogen can remain trapped in ice at the low temperatures of interstellar space. The ice acts as a cage, preventing escape. Only when the ice warms significantly does the hydrogen begin to vent. The process is self-limiting. Once you heat the outer layers enough to release their hydrogen, those layers protect the interior from further warming, allowing the deeper reserves to remain locked in place until the object moves even closer to the Sun. This created a testable prediction. If the hydrogen hypothesis is correct, we should find more dark comets. Objects in our own solar system that show subtle acceleration without visible outgassing. Objects that never traveled between the stars but still accumulated enough trapped hydrogen through local radiation processing to produce measurable thrust. The prediction proved correct. By 2024, astronomers had identified those 14 additional objects. They weren't interstellar visitors. They were solar system natives. But they showed the same signature: acceleration without a coma. The dark comet population existed. This discovery transformed Oumuamua from a unique anomaly into the first example of a broader phenomenon. The characteristics that seemed so bizarre in 2017 now appeared as natural consequences of radiation processing in ice-rich bodies. The mystery hadn't required new physics. It required better understanding of chemistry that occurs routinely in space. Still, questions remained. Not every detail fit perfectly. The hydrogen model assumed Oumuamua began as a relatively normal comet, water-rich and similar to objects in our own Kuiper belt. But could such an object really survive the journey? Interstellar space subjects traveling bodies to constant erosion. Dust impacts, radiation damage, slow sublimation even in the cold between stars. Would a comet remain intact over hundreds of millions of years? Some researchers proposed alternatives. Perhaps Oumuamua wasn't a pristine comet but a fragment of something larger. Tidal forces near a star can rip bodies apart, creating elongated shards that get ejected into interstellar space. This tidal fragmentation scenario explained both the unusual shape and the population statistics. Computer models showed that stellar encounters efficiently produce Oumuamua-sized fragments, potentially accounting for the vast number of interstellar objects that must exist. Another possibility emerged from studies of Pluto and similar bodies in our outer solar system. These worlds have surfaces rich in nitrogen ice. When nitrogen ice sublimates, it produces thrust without creating a dusty coma. Could Oumuamua be a fragment of a Pluto-like exoplanet, broken apart and ejected from its system? The nitrogen ice hypothesis offered a different path to the same observational outcome: acceleration without visible outgassing. Each theory had strengths. Each had weaknesses. The hydrogen outgassing model explained the acceleration with well-understood chemistry but required the object to survive an improbably long journey. The nitrogen ice hypothesis invoked familiar materials from our own solar system but required a very specific origin. The tidal fragmentation scenario explained the shape and population but added complexity to the formation story. What became clear was that scientists weren't choosing between one correct answer and several wrong ones. They were mapping a solution space. Multiple mechanisms might produce dark comets. Some interstellar objects might be hydrogen-rich water ice bodies. Others might be nitrogen ice fragments. Still others might be tidal shards or ejected planetesimals with entirely different compositions. The discovery of the 14 solar system dark comets supported this diversity. These objects showed a range of characteristics. Some were large, some small. Some showed strong acceleration, others weak. The dark comet population wasn't uniform. It was a category defined by behavior, not composition. This realization changed how astronomers thought about Oumuamua. The object wasn't a singular puzzle requiring a singular solution. It was one example from a diverse population. Understanding that population meant understanding multiple formation pathways, multiple compositional possibilities, multiple evolutionary histories. By 2023, the scientific consensus had shifted. Most researchers agreed that Oumuamua was natural, not artificial. Most favored the hydrogen outgassing explanation, though alternatives remained viable. The alien artifact hypothesis, while not completely discarded, had moved to the margins. Not because it was definitively disproven, but because simpler explanations proved sufficient. Yet something important had emerged from the controversy. The artifact hypothesis, however unlikely, forced scientists to examine their assumptions. It pushed researchers to develop more sophisticated models, to consider possibilities they might otherwise have dismissed. The debate itself advanced understanding, even as the community converged on conventional answers. Oumuamua's legacy extended beyond its own mystery. It proved that interstellar objects visit our solar system regularly. Before 2017, this was theoretical. After Oumuamua, it became observational fact. The galaxy is filled with wandering bodies, ejected from their birth systems, traveling between the stars. We inhabit a shooting gallery of interstellar debris. How many of these objects pass through undetected? The calculations are sobering. Astronomers estimate that several Oumuamua-sized objects cross Earth's orbit each year. Within Neptune's orbit, about 10,000 interstellar visitors might be present at any given moment, each spending roughly a decade in the inner solar system before departing. Most go unnoticed. They're small, dark, and moving fast. Only recently have telescopes become powerful enough to catch them. Pan-STARRS found Oumuamua essentially by accident, during a routine survey for near-Earth asteroids. The discovery depended on luck as much as capability. that luck won't hold forever. Future discoveries depend on systematic surveys, not chance encounters. The Vera C. Rubin Observatory, currently under construction in Chile, will change everything. Its wide-field telescope will scan the entire visible sky every few nights, detecting faint, fast-moving objects that current instruments miss. When Rubin becomes operational, astronomers expect to find dozens of interstellar visitors annually. Maybe hundreds. This transforms Oumuamua from a singular mystery into the first data point in a much larger study. What percentage of interstellar objects are dark comets? How many show visible cometary activity? What's the distribution of shapes, sizes, compositions? These questions can't be answered with a sample size of 1. They require population statistics. The second confirmed interstellar visitor arrived in August 2019. Gennady Borisov, a Crimean amateur astronomer, spotted it using a telescope he built himself. The object, designated 2I/Borisov, behaved exactly like a traditional comet. It had a prominent coma, a visible tail, and showed clear signs of outgassing. Spectroscopic analysis revealed familiar molecules: water, carbon monoxide, cyanogen. Borisov looked unremarkable. It could have been a solar system comet if not for its hyperbolic trajectory. The contrast was striking. Oumuamua, strange shape, no coma, mysterious acceleration. Borisov, normal appearance, standard cometary behavior, straightforward chemistry. Two interstellar objects, completely different characteristics. This diversity suggested that interstellar space contains the full spectrum of small body types found in planetary systems everywhere. Then, in July 2025, a third visitor appeared. Free-I/Atlas entered the inner solar system moving even faster than its predecessors, with a hyperbolic excess velocity of 58 kilometers per second. For comparison, Oumuamua arrived at 26 kilometers per second, Borisov at 32. Atlas was racing through our neighborhood at truly remarkable speed, suggesting it originated from a more energetic ejection event or had been wandering the galaxy for an exceptionally long time. Free objects. Three different stories. The sample remains tiny, but patterns begin emerging. Interstellar visitors aren't uniform. They vary as much as the planets and moons orbiting our own sun. Some are rocky, some icy. Some tumble chaotically, others rotate smoothly. Some outgas visibly, others remain dark and enigmatic. What can we learn from these wanderers? Each interstellar object carries information about its birth system encoded in its composition, structure, and trajectory. Studying them provides a way to probe planetary systems without actually traveling to them. The chemistry of a dark comet might reveal the ice composition of distant Kuiper belt analogs. The shape might indicate formation mechanisms or collision histories. The trajectory could hint at the architecture of the system that ejected it. But there's a deeper question: where do these objects come from? Backtracking Oumuamua's path proved difficult because the object had been traveling for so long that uncertainties accumulated. Initial calculations suggested it came from the general direction of Vega, but the star wasn't in that position 300,000 years ago when Oumuamua would have passed through. The object's velocity relative to nearby stars suggested it had been wandering the galaxy for eons, possibly orbiting the galactic center multiple times. This implies Oumuamua didn't come from any particular star. It came from the galaxy itself, from the general population of ejected debris circulating between stellar systems. Most interstellar objects probably share this origin. They're not messengers from specific neighboring stars but rather samples from the galaxy's collective planetary systems, mixed and redistributed over billions of years. The ejection mechanisms that create these wanderers tell us about planetary system dynamics. Giant planets are particularly efficient at flinging smaller bodies into interstellar space. When gas giants migrate inward during a system's early history, they scatter planetesimals in all directions. Some fall into the star, some remain in stable orbits, and some achieve escape velocity. Systems with multiple giant planets in unstable configurations produce even more ejecta as the massive worlds gravitationally jostle each other and everything nearby. This process isn't gentle. Computer simulations show that young planetary systems are violent places. Planets migrate, orbits cross, collisions occur. The debris generated during this chaotic phase gets scattered throughout the galaxy. Every stable planetary system we observe today probably ejected thousands or millions of smaller bodies during its formation. Those objects are still out there, drifting between the stars. The total population must be staggering. If each star system produces even a modest amount of ejecta, and there are hundreds of billions of stars in the galaxy, the cumulative number of interstellar objects reaches astronomical figures. Some estimates suggest there might be more interstellar wanderers than stars in the observable universe. The space between stars isn't empty. It's filled with frozen remnants of planetary formation, ancient debris from long-settled systems. Most of these objects will never be detected. They're small, dark, and scattered across vast distances. Only those that happen to pass near our sun become visible, and only recently have our telescopes been good enough to spot them. We're sampling an invisible ocean of material using a very small net. What about missions to intercept these visitors? After Oumuamua's discovery, several groups proposed spacecraft concepts designed to catch up with the object before it left the solar system forever. The Initiative for Interstellar Studies launched Project Lyra, examining various mission architectures with different launch dates, propulsion systems, and flight times. The proposals ranged from 5-year missions using powerful chemical rockets and gravity assists to 25-year journeys using solar sails or nuclear propulsion. Every scenario faced the same fundamental problem: speed. Oumuamua was already moving faster than any spacecraft we'd ever launched, and it was accelerating away from the sun. Catching it would require velocities we can't currently achieve. Even our fastest probes, like the Parker Solar Probe or New Horizons, couldn't match Oumuamua's trajectory. Intercepting it would demand technologies that don't yet exist: advanced propulsion systems, efficient energy sources, materials that can withstand extreme velocities. The window for such a mission has closed. Oumuamua is now beyond Jupiter's orbit, heading toward the outer solar system boundary. In a few more years, it will pass Neptune and enter the scattered disk region. Eventually, it will leave the Sun's gravitational influence entirely and return to interstellar space, continuing its billion-year journey through the galaxy. We'll never see it again. But future interstellar visitors present new opportunities. If we know they're coming, we can prepare. A spacecraft could be pre-positioned in the outer solar system, waiting on standby. When an interstellar object is detected, the spacecraft could launch toward an intercept point. This requires rapid response capabilities and flexible mission planning, but it's technically feasible with sufficient preparation. The scientific payoff would be enormous. A close-up examination of an interstellar object would reveal details impossible to obtain from telescopic observations. We could measure its exact composition, study its internal structure, examine its surface features, and directly sample any outgassing. These measurements would answer questions that spectra and light curves can only hint at. Imagine a spacecraft approaching one of these dark comets. Cameras would resolve surface details, craters from ancient impacts, layers of different materials, maybe even organic compounds preserved in pristine condition. Spectrometers would analyze the chemistry of any gases being released. Radar would probe beneath the surface, mapping internal structure. If the object was tumbling, as Oumuamua appeared to be, instruments could determine why, possibly finding evidence of the collision that set it spinning billions of years ago. Such a mission would transform our understanding. We'd move from inference and modeling to direct observation. The data gathered from one interstellar object would inform interpretations of all the others. Composition measurements would calibrate spectroscopic observations. Surface features would constrain formation theories. Every measurement would reduce uncertainty, replacing speculation with knowledge. Until that happens, we continue learning from a distance. Each new detection adds information. Each observation refines models. The population statistics improve as more objects are found. Slowly, the picture becomes clearer. Interstellar space isn't uniform or empty. It's structured, populated, dynamic. These wandering bodies connect stellar systems across the galaxy, mixing materials, distributing elements, perhaps even transporting organic molecules between stars. Could life itself travel on these objects? The idea isn't new. Panspermia, the hypothesis that life spreads between worlds via natural processes, has been discussed for over a century. Interstellar objects provide a potential mechanism. If microorganisms can survive inside comets, shielded from radiation and cold, they might persist during the journey between stars. Upon entering a new system, if the object breaks apart or impacts a planet, those organisms could be delivered to fresh environments. The hypothesis remains speculative. No evidence currently supports it. But the discovery that interstellar objects are common makes the idea slightly less implausible. If microbes can survive the journey, why haven't we found them yet? The answer comes down to probability and detection limits. Even if panspermia occurs, the odds of finding direct evidence remain vanishingly small. Space is vast. The number of potential landing sites across billions of years dwarfs our capacity to search. A microorganism delivered to early Earth would have mixed into existing populations, its extraterrestrial origin erased by evolution. No signature would remain. DNA mutates. Lineages diverge. After 4 billion years, tracing any organism back to an interstellar source becomes impossible. Testing the hypothesis requires different approaches. Scientists can examine meteorites for signs of preserved biological material. Some contain organic compounds, amino acids, even structures resembling microbial fossils. But proving those structures are genuinely biological and not just mineral formations remains contentious. The debate continues, unresolved. Another method involves studying extremophiles, organisms that thrive in conditions once thought incompatible with life. Deep-sea vents. Frozen Antarctic lakes. Acidic hot springs. If life can persist in these environments, perhaps it could survive inside a comet. Laboratory experiments expose bacteria to simulated space conditions, vacuum, radiation, extreme cold. Some survive. Not all, but enough to suggest the possibility isn't ridiculous. Still, survival in a lab differs from surviving millions of years in actual interstellar space. The radiation dose accumulates. Cosmic rays don't just hit the surface, they penetrate deep. Over geological timescales, even shielded organisms would suffer catastrophic DNA damage. Repair mechanisms might fail. The question isn't whether life could survive briefly in space, which we know it can, but whether it could remain viable across the immense timescales required for interstellar travel. That's where the numbers get uncomfortable. Oumuamua's journey probably lasted tens to hundreds of millions of years before encountering our solar system. Could any organism, even in a dormant state, withstand that duration? Current biology suggests no. But current biology reflects Earth-based life, evolved under specific conditions. Extraterrestrial microbes might possess biochemistry we haven't imagined. Assuming they follow our rules could be a mistake. What if life doesn't need to survive the entire journey? Suppose organisms enter a state so dormant that biological time effectively stops. Metabolism ceases. Molecular processes freeze. In this state, radiation damage still occurs, but without active cellular function, perhaps degradation slows enough to permit survival. Upon arrival, if conditions allow, the organisms revive. Speculative, yes. Impossible, no. The discovery of dark comets adds another layer. These objects outgas without visible comas, releasing material we can't easily observe. If that material includes organic molecules or even preserved biological structures, we'd miss them with current detection methods. Spectroscopy identifies molecular signatures, but only if concentrations exceed detection thresholds. Trace amounts of complex organics could be present, unnoticed. Future missions might change that. If we intercept an interstellar object and conduct direct sampling, instruments could analyze material with far greater sensitivity than telescopes allow. Mass spectrometers would detect minute quantities of organic compounds. Microscopes could examine physical structures. If biosignatures exist, we'd find them. But what counts as a biosignature in this context? On Earth, we recognize life through specific patterns: cell membranes, metabolic byproducts, isotopic ratios indicating biological processing. Extraterrestrial life might not follow those patterns. It could use different chemistry, different structural organization, different energy sources. Identifying it requires recognizing life in forms we haven't encountered. This brings us back to Oumuamua and what it represents beyond itself. Every interstellar object carries information about its origin. The composition reveals conditions in its parent system. The trajectory indicates ejection mechanisms. The surface features record impacts and thermal history. Collectively, these objects map the galaxy's planetary systems in ways traditional astronomy cannot. Think of it as archaeology on a galactic scale. Each wandering fragment holds clues about worlds we'll never visit. A rocky composition suggests formation in an inner system. Icy material points to outer regions. Organic-rich surfaces imply carbon chemistry similar to our own. Over time, as the catalog grows, patterns will emerge. We'll begin to understand what planetary systems typically produce, how often ejection occurs, and what conditions lead to interstellar wandering. The statistics matter profoundly. If most interstellar objects resemble solar system bodies, it suggests planet formation follows universal principles. If they differ significantly, it implies greater diversity than current models predict. Either outcome teaches us something fundamental about how matter organizes into planets. Oumuamua's composition remains debated precisely because we couldn't measure it directly. Spectroscopic observations provided limited information. The red color suggests organic material or irradiated ice, but doesn't confirm either. The lack of a coma argues against active ice sublimation, but the hydrogen outgassing theory explains that through a mechanism requiring no visible ejecta. We're left with competing interpretations, none definitively proven. That ambiguity frustrates scientists accustomed to clear answers, but it's also instructive. It reveals how little we can learn from brief observations of fast-moving objects at extreme distances. It highlights the need for better detection systems, faster response times, and ideally, direct sample return missions. The Vera Rubin Observatory, scheduled to begin operations soon, will dramatically increase detection rates. Its wide-field survey will scan the entire visible sky every few nights, identifying transient objects far faster than current systems. When an interstellar visitor appears, we'll know within hours instead of weeks. That early warning provides time to mobilize resources, point additional telescopes, and potentially launch intercept missions if spacecraft are ready. Preparation matters. The next Oumuamua could appear tomorrow or a decade from now. Without standby missions, we'll repeat the same pattern: detect, observe briefly, watch it leave. With preparation, we could deploy a probe rapidly, reaching the object while it's still within range. The technology exists, implementation requires funding and institutional commitment. Consider what we'd learn from even a flyby mission. High-resolution imaging would reveal surface details invisible from Earth. We'd see craters, fractures, color variations, maybe even layered structures indicating different formation periods. Spectrometers would analyze reflected and emitted light at close range, providing compositional data far exceeding anything ground-based telescopes can achieve. If the object outgassed, instruments could sample the ejecta directly, measuring isotopic ratios and detecting trace compounds. A more ambitious mission might include a lander. Touching down on a tumbling interstellar object presents enormous technical challenges, but it's theoretically possible. The lander would drill into the surface, collecting samples for analysis. Instruments would measure temperature, density, and mechanical properties. If organic material existed, we'd identify it with certainty. Such a mission would cost billions and require years of development. But the scientific return would justify the investment. We'd obtain ground truth data for an entire class of objects, calibrating all future observations. Every subsequent detection would benefit from that knowledge. Until then, we rely on inference. Each new interstellar object adds data points. 2I Borisov, the second confirmed visitor, looked like a normal comet, complete with coma and tail. Its behavior matched expectations for an icy body. Spectroscopy revealed familiar molecules: water, carbon monoxide, cyanide compounds. Nothing unusual except its origin. That normalcy was almost disappointing. After Oumuamua's strangeness, scientists half expected every interstellar object to defy explanation. Borisov proved otherwise. Most visitors probably resemble solar system counterparts. Oumuamua might represent an outlier, an unusual case rather than the norm. Yet outliers matter scientifically. They reveal edge cases, boundary conditions where standard models break down. Understanding why Oumuamua behaves differently teaches us about processes we hadn't considered. The hydrogen outgassing mechanism, for instance, emerged from trying to explain its acceleration. That mechanism might occur in solar system comets too, just unnoticed because other processes dominate. Studying the unusual illuminates the typical. The third confirmed visitor, 3I Atlas, arrived with hyperbolic excess velocity higher than either predecessor. Its trajectory suggests an origin farther from its parent star or ejection via a more energetic mechanism. As the sample size grows, we'll begin classifying these objects by properties: velocity, composition, size, rotation state. Patterns will emerge. Some might correlate with ejection mechanisms or parent system characteristics. This cataloging process mirrors early astronomy. Centuries ago, astronomers classified stars by brightness and color. Over time, those classifications revealed underlying physics, stellar mass, temperature, age. Similarly, classifying interstellar objects will eventually expose the processes that created them. We're in the data-gathering phase, accumulating observations that future scientists will interpret with better models and theories. Oumuamua opened that door. Before its discovery, interstellar objects were theoretical possibilities. Now they're confirmed reality, observable and measurable. The field has matured from speculation to empirical science. Telescopes scan specifically for these visitors. Detection algorithms prioritize hyperbolic trajectories. When the next one appears, we'll be ready to observe it properly. And make no mistake, more will appear. The galaxy contains hundreds of billions of stars, each potentially hosting planetary systems that eject material. The volume of space between stars is immense, but so is geological time. Over millions of years, ejected objects disperse throughout the galaxy, creating a background population that occasionally intersects with our solar system. We're just beginning to sample that population. Statistical analysis becomes possible with sufficient numbers. Right now, 3 confirmed detections don't constitute a robust dataset. We need dozens, ideally hundreds, before drawing firm conclusions about the interstellar population. But those numbers are coming. The Vera Rubin Observatory, scheduled to begin operations soon, will scan the entire visible sky every few nights. Its wide field of view and sensitive detectors make it ideal for catching fast-moving transients. Simulations predict it could detect several interstellar objects annually, transforming the field from novelty to systematic study. When that happens, the questions shift from, "What is this thing?" to, "What does the distribution tell us?" If most objects resemble Borisov, we'll conclude that standard cometary ejection dominates. If many match Oumuamua's profile, the hydrogen outgassing mechanism might be common. If we find objects with characteristics matching neither, we'll know our models remain incomplete. Each detection also constrains formation conditions in other stellar systems. Composition reflects the temperature and pressure where objects formed. Rocky bodies suggest formation near their star, where volatile ices couldn't survive. Icy bodies indicate formation farther out, where temperatures remained low. The ratio between these types reveals something about typical planetary system architecture. Do most systems concentrate rocky material inward and icy material outward, like ours? Or do other configurations dominate elsewhere? Velocity distributions matter too. Objects ejected from young, unstable systems might carry higher speeds than those from mature, settled systems. Measuring entry velocities for many objects could reveal the typical dynamical state of planetary systems throughout the galaxy. We're essentially using these visitors as probes, sampling conditions billions of kilometers away and millions of years ago. There's also the contamination question. Not every object with unusual properties comes from another star. Some might originate in the Oort cloud, that distant reservoir of comets surrounding our solar system. Distinguishing between true interstellar objects and weird locals requires precise trajectory measurements. Oumuamua's hyperbolic orbit left no doubt about its extrasolar origin. Future objects might prove more ambiguous, especially if observed less completely. The dark comet classification adds another layer. 14 objects exhibiting non-gravitational acceleration without visible outgassing now populate this category. Oumuamua pioneered it, but the class has expanded. Understanding what makes these objects behave differently matters for both solar system science and interstellar studies. If the mechanism operates locally, it probably operates elsewhere too. Consider what this means for our understanding of planetary system evolution. Every star forms from a collapsing molecular cloud, creating a disk of material that gradually coalesces into planets. During that process, countless small bodies form, most destined to be ejected through gravitational interactions with larger planets. Those refugees become the interstellar population, drifting through the galaxy until chance encounters with other stars. That population carries signatures of its origins. Chemical composition reflects the original cloud's makeup. Isotopic ratios preserve information about nucleosynthesis in previous stellar generations. Physical structure reveals formation processes. Every interstellar object is essentially a messenger, carrying information from distant systems that will never visit directly. Oumuamua's red coloring, for instance, results from cosmic ray bombardment over hundreds of millions of years. That reddening process occurs in all interstellar objects exposed to radiation. The degree of reddening indicates exposure time, which constrains when the object was ejected. Detailed spectroscopy could potentially identify the parent star's metallicity based on composition. Future missions might attempt rendezvous with these visitors, not just flyby observations. Imagine a spacecraft already in position, waiting for the next interstellar object to arrive. When one appears, the spacecraft adjusts trajectory to match velocity, effectively hitchhiking alongside. That scenario requires predicting arrival times and trajectories well in advance, but it's technically feasible with sufficient warning. The payoff would be transformative. Continuous observation over weeks or months would capture details impossible from Earth. Surface mapping at high resolution. Thermal measurements across day-night cycles. Compositional analysis of any outgassing, even if too faint for ground telescopes. Mass determination through precise tracking of the spacecraft's position relative to the object. Some proposals suggest interceptor missions using high-speed spacecraft that could launch on short notice. When a new object appears, the interceptor launches within days, reaching velocity sufficient to catch up before the visitor escapes. That requires keeping spacecraft ready and having launch capabilities on standby, significant logistical challenges but not impossible. The broader context matters. Oumuamua demonstrated that interstellar objects aren't just theoretical curiosities but observable reality. That confirmation changed how we think about the galaxy. Instead of isolated stellar systems separated by vast emptiness, we now know the space between stars contains structure, a diffuse population of wandering bodies, each with a story to tell. These objects might even play roles in panspermia, the hypothesis that life spreads between star systems. If interstellar objects can carry organic molecules, and if some impacts occur on habitable planets, biology could potentially transfer across interstellar distances. Oumuamua showed no signs of organic material, but we barely observed it. Future objects might reveal complex chemistry preserved in ice. The statistical likelihood of such transfers remains debated. Even if interstellar objects frequently carry organics, the probability of one impacting a planet with suitable conditions, at the right time in that planet's development, seems vanishingly small. But over billions of years and countless objects, low-probability events eventually occur. What we know for certain is that the galaxy is more interconnected than we realized. Material doesn't stay confined to individual stellar systems. It escapes, travels, and occasionally arrives somewhere new. Oumuamua proved that exchange happens. The rate, composition, and implications remain active research questions. As observational capabilities improve, we'll catch these visitors earlier in their approach. Earlier detection means more observation time. More observation time yields better data. Better data enables more sophisticated analysis. That positive feedback loop will accelerate our understanding rapidly once the Rubin Observatory comes online. The field has matured dramatically since 2017. Initial confusion about Oumuamua's nature has given way to plausible physical models. The hydrogen outgassing theory fits observations without requiring exotic physics or artificial origins. It's almost certainly correct, though confirmation awaits additional examples exhibiting similar behavior. That resolution demonstrates how science processes anomalies. Initial observations confound existing models. Wild hypotheses emerge, including alien artifacts and hydrogen icebergs. Detailed analysis eliminates the impossible. Eventually, a natural explanation emerges that accounts for all observations while requiring minimal new physics. The explanation might seem obvious in hindsight, but getting there required genuine intellectual work. Oumuamua will never return. It's currently beyond Neptune's orbit, moving at 70,000 miles per hour toward interstellar space. In a few centuries, it will exit the Oort cloud entirely, resuming its journey through the galaxy. Millions of years from now, it might pass near another star, briefly warming before continuing onward. That cycle could repeat indefinitely, a cosmic wanderer with no permanent home. But it left its mark here. It forced us to reconsider what's possible, to expand our catalog of phenomena, to prepare for future visitors. The next interstellar object won't surprise us the same way. We'll know what to look for, which instruments to use, which measurements matter most. That preparation will pay dividends. The universe contains wonders we've barely begun to catalog. Oumuamua represents just one category: interstellar debris from planetary system formation. Other categories surely exist. Rogue planets ejected from their systems. Fragments from stellar collisions. Debris from supernovae. Each carries information about processes we can't easily observe directly. Our solar system sits in a river of material flowing through the galaxy. Occasionally, something distinctive floats past, and we have a brief window to study it. Oumuamua was the first we recognized. It won't be the last. Every future detection adds to our understanding, building toward comprehensive knowledge of what exists between the stars. That knowledge reshapes how we view our place in the cosmos, not isolated, but connected to the broader galactic ecosystem. The stream of interstellar visitors flowing through our solar system will continue long after we stop looking. Oumuamua taught us that much. Right now, somewhere beyond Neptune's orbit, another wandering fragment might be passing through, invisible to our instruments, too faint to register against the background stars. We wouldn't know. Most objects slip past unnoticed, their presence inferred only through statistical models predicting how many should exist based on the few we've caught. That invisibility bothers some researchers. The idea that remarkable objects traverse our neighborhood constantly, carrying information from distant systems, yet remain undetected feels like a wasted opportunity. But frustration doesn't change the physics. Detection requires light, and most interstellar debris reflects too little to register at the distances involved. We catch the lucky few that pass close enough and orient favorably when someone happens to be looking. The rest remain anonymous. Still, the detection rate will improve. Technology advances. Survey telescopes grow more sensitive. Algorithms become smarter at distinguishing genuine objects from noise. The trickle of discoveries will become a stream, then perhaps a flood. When that happens, Oumuamua's uniqueness will fade. It'll become entry 1 in a catalog containing hundreds or thousands of similar objects, each with its own trajectory and characteristics. What made Oumuamua special wasn't its strangeness alone but its timing. It arrived when our capabilities had just barely reached the threshold to detect it. A decade earlier, the Pan-STARRS telescope didn't exist. The survey that found Oumuamua wasn't running. We would have missed it entirely. A decade later, with better instruments, we might find dozens like it annually. Oumuamua occupied that narrow window where detection was possible but rare, making it historically significant regardless of its physical properties. The debates about its nature, however heated they became, reflect healthy scientific process. When observations don't match expectations, controversy follows. Different researchers favor different explanations. Papers get published arguing contradictory positions. Eventually, evidence accumulates until consensus emerges. That's how it's supposed to work. Oumuamua generated more controversy than most discoveries because the stakes felt higher. An interstellar visitor suggested connection to other worlds, to planetary systems beyond our own. The possibility, however remote, that it might be artificial captured public imagination in ways that typical astronomical discoveries don't. But the artifact hypothesis, while generating headlines, probably taught us less than the more mundane explanations. The hydrogen outgassing theory emerged from researchers asking what happens to ice during million-year journeys through space. That question has implications beyond Oumuamua. It applies to any icy body exposed to cosmic radiation, including objects in our own Oort cloud. The mechanism might operate routinely in dark comets throughout the galaxy. Understanding it improves our models of how volatiles behave under extreme conditions. Science advances through such incremental improvements more than through revolutionary discoveries. Oumuamua forced refinement of cometary models, better understanding of radiation processing, more sophisticated analysis of non-gravitational forces. Those advances benefit solar system science as much as interstellar studies. The next time a Kuiper belt object shows unexpected acceleration, researchers will have better tools to analyze it, thanks to work prompted by Oumuamua. The bigger picture matters more than individual objects. Oumuamua confirmed that interstellar space contains structure, that material moves between stellar systems, that our solar system participates in a galactic ecosystem of debris exchange. Those realizations shift perspective. We're not isolated. Our sun isn't a lonely island in an empty void. It's one star among hundreds of billions, all shedding material that mixes and redistributes over cosmic timescales. That mixing might have biological implications. If organic molecules survive on interstellar objects, they could seed chemistry on planets that lack local sources. Impacts might deliver complex compounds, jump-starting prebiotic evolution. The hypothesis remains speculative, but it's no longer absurd. We know the delivery mechanism exists. Whether it matters for life's origins requires evidence we don't yet have. Future missions might provide that evidence. Intercepting an interstellar object and analyzing its composition directly would reveal whether organics commonly survive the journey. Mass spectrometry could identify specific molecules. Isotopic analysis could determine their origin. If we found amino acids or other biologically relevant compounds, it wouldn't prove panspermia but would make the hypothesis more plausible. The technical challenges remain formidable. Matching velocity with a fast-moving object requires propulsion systems that don't currently exist at the necessary scale. Chemical rockets can't reach the speeds involved. Nuclear propulsion might work but faces political and engineering obstacles. Solar sails offer an alternative, using radiation pressure for continuous acceleration, but development remains in early stages. None of these technologies will be ready tomorrow or even next decade. That's fine. The science doesn't require immediate missions. We can learn enormous amounts from ground-based observations as detection rates increase. Each new object adds data. Patterns emerge. We start to understand what's typical versus what's unusual. That statistical foundation proves essential before investing billions in spacecraft that might not reach their targets. Patience matters in astronomy. The timescales are long. Oumuamua appeared and departed within months, but understanding what it was took years. Full consensus might take longer still. That's normal. Science moves deliberately, testing ideas against evidence, discarding what doesn't fit, refining what remains. The process seems slow to outsiders accustomed to instant answers, but it produces reliable knowledge that withstands scrutiny. What we've learned definitively is that interstellar objects exist, that they visit regularly, and that they're detectable with sufficient effort. Everything else remains provisional to varying degrees. The hydrogen outgassing explanation looks solid but awaits confirmation through additional examples. The dark comet classification seems robust, with 14 members and counting. The population statistics remain uncertain, bounded by models rather than direct measurement. Those uncertainties don't diminish what's been achieved. 7 years ago, interstellar objects were hypothetical. Now they're empirical facts, observed and measured. The field has progressed from speculation to data collection. That transition marks genuine scientific advancement, even if many questions remain unanswered. As more objects appear, the questions will shift. We'll stop asking whether interstellar visitors exist and start asking what their properties reveal about galactic conditions. We'll use them as probes, sampling planetary systems too distant to study directly. We'll build catalogs, classify types, correlate properties with trajectories. Gradually, the picture will sharpen. Oumuamua won't be forgotten. First detections rarely are. It'll remain historically significant, the object that opened the door to an entire field of study. Future discoveries might prove more scientifically valuable, providing clearer data or revealing unexpected phenomena. But Oumuamua will always be the one that showed us interstellar visitors are real. And somewhere out there, right now, another fragment is approaching. Maybe we'll detect it. Maybe it'll slip past unnoticed like so many others. Either way, the galaxy continues its ancient process of mixing and redistributing material between stars. We've finally developed tools to observe that process directly. That capability matters more than any single object, more than solving Oumuamua's specific mysteries. We're learning to read the galaxy's story written in the debris flowing between stellar systems. That story extends backward billions of years and forward far beyond human timescales. We're just beginning to understand the opening chapters.